In this first video on nonparametric measures of correlation, we will start with Spearman's rank order correlation coefficient. We use this test when we have sets of ordinal data. In other words, the data in each group are ranked. Most often in correlation, we have interval level data, and we use a process that you're going to learn about next week. So you might be wondering why we went out of order with our textbook chapters this week. I think you will more easily grasp nonparametric measures of correlation with last week's work with nonparametric measures fresh in your mind. The downfall is we are jumping into correlation without the benefit of the background in Chapter 10. Therefore, as noted on Blackboard, you should take a moment to read the following sections in Chapter 10: Strength of correlation, Direction of correlation, and the correlation coefficient. To illustrate the Spearman's rank order correlation coefficient, I will use a question from your book that reads, the following 5 students were ranked in terms of when they completed their exam. 1 equals first to finish, 2 equals second to finish, and so on, and were given an exam grade by an instructor. Test the null hypothesis of no relationship between grade, x, and length of time to complete the exam, y. That is, compute a rank order correlation coefficient and indicate whether it is significant. So the formula for Spearman's rank order correlation coefficient is right over here, and I've set up a table on the left to be able to gather all the information that we're going to need to complete the formula. So I have the data here for x, which are the scores on the exam. And I also have the data for y, which is the rank order of how long it took them to complete the exam. 1 meaning first to finish, all the way down to 5 meaning last to finish. And we don't have anything to do for y because it's already ranked, but we do need to assign a rank of 1 to 5 for the exam scores. And that's why I have this X rank column here, because I knew I would have to find the rank order for the exam scores. And since 1 on the variable y indicates the least amount of time it took to take an exam, I'm going to rank order my exam scores from least to greatest as well. So the lowest score is 53, so I'm going to give that a rank of 1. The second lowest score is 70, so I'll give that a rank of 2. And the third lowest score is 85. So easy so far. But then when we hit the fourth score, we have a tie between 91 and 91. And in this case, we have to apply the rule for what we do when there are tied numbers. And that is, we're going to put an equal sign, and we're going to add the 2 ranks that these scores would represent. So in this case, it's 4 and 5. So 4 plus 5. So I'm adding the 4th rank and the 5th rank. And then I'm going to divide that by the number of ties that we have. So we have 2 scores that tie, so I'm going to divide it by 2. And that gives us a score of 4.5, and each of these scores is going to share that rank of 4.5. And that's how we solve that problem. Now, if we had a score that was higher than 91 in this group, instead of going to have that score be number 5, that score would be number 6, because these 2 scores, even though they say 4.5, they represent the 5th and the 4th and the 5th ranks. And so the next score, if we had another one higher, would be ranked with a 6. And now that we have our ranks, we're going to find the difference between the ranks. And as always, our deviation scores should sum to 0, so let's do that very quickly. The rank of 1 minus the rank of the other, and I'm going to draw down. And I'm going to sum them up just to see, make sure that I've done it right. Yes, it sums to 0, so these deviation scores are correct. And then I'm going to square the deviation scores, as we've done before. And I am going to need the sum of these squared deviations over here, so I will do that as well. So the sum of our squared deviation is 8.5. And now we have everything we need to plug into this formula. And what I've done is I've separated out the steps to the formula here to make it a little bit easier. And so for the first step, we're going to multiply the number 6 times the sum of the squared deviations, and that gives us 51. In the second part of the formula, we're going to take the n, which is 5. We have 5 people in this study, and we're going to multiply 5 times 5 squared minus 1. So easy enough. I'm going to put equals and then a 5 because that's our n. And in parentheses, I'm going to do a 5 and then a caret and a 2 to square that 5 minus 1. All right. Oh my, what did I not do? Something I didn't do. Okay, but I know I have the right number because 25 minus 1 is 24, and 24 times 5 is going to give us 120. So we are on the right track. And finally, to get our correlation coefficient to show the relationship, we're going to take the number 1 and we're going to subtract we're going to subtract this division term. So here we go. Equals 1 minus, and I'm going to put this in a parentheses, and I have the first, the numerator, over the denominator, and hit return. What am I doing? But I got the right answer again, which is 0.58. You watching this, you probably know what I'm doing. I'm doing it so fast I'm not seeing it. Anyway, 0.58 is our correlation coefficient. And as correlations go, 0.58 seems solid. 58% of the variation in scores can be explained by the relationship between the two variables. However, is it statistically significant? To find out, we need to compare our correlation to a table in Appendix C, and I'm going to pull that up right now, entitled Critical Values of R sub S. I lost it. That's the Spearman rank order correlation coefficient at the 0.05 and 0.01 levels of significance. So it's this one right here on the right. This table over here we're going to go back to when we look at chapter 10. But anyway, we're here. So we're going to use the number of ranks as our n, which is 5. And drawing over to the 0.05 significance level, we see that our value must exceed 1.0. Well, that's just not going to happen, is it? Because correlations go from -1 to +1. It's not going to go above 1. So I know right now that this is going to be considered not significant. I'm going to retain the null in this case. And as you can probably figure out, with a sample size of 5, we're just not going to be able to find significance in this case. But we did try, so there you go. So the conclusion we can draw is that there's not a relationship between exam scores and the order in which students completed their exams. Any similarities that we're seeing or any relationship we're seeing is simply due to chance. My guess is if we added numbers of participants, we might see something different or we might not. But just with this small number of participants, we're just not going to see anything. So that's Spearman's rank order correlation coefficient. It's not often used because we don't often seek to find correlation with ordinal data. But if ordinal data is all you have to work with, this test is your go-to. Unless you have cross-tabulated ordinal variables, in other words, which will be discussed in the next video on Goodman's and Kruskal's gamma.